Hi, hello everyone. My name is Yingjun, and today I'm super excited to talk about the mitigating the impact of the state management in the cloud stream processing systems. So if you have any experience working with stream processing systems, you know that state management can be the key challenge. And in this talk, I will just focus on, if we want to build a stream processing in the cloud, then how we can solve this problem and what kind of state management mechanism we can adopt to ensure the latency and the throughput of the system. So my name is Yingjun Wu, and I'm the founder at Rising Wave Labs. I'm also the so-called CEO or the Chief Everything Officer. So I have actually had an engineering background, but nowadays I work across different functions like engineering, product, marketing, sales, and many others. Before starting this company, I was at AWS Redshift and IBM Research Almaden. I obtained my PhD in the database system domain and as well as the stream processing. So I feel that I'm super lucky to have the chance to, work on these two database and the stream processing domains and try to get the best of both worlds in by building a next generation database system. So just one slide about what we're building. What we're building is a system called Riding Wave. It's a distributed SQL streaming database. Basically, you can think of it like a database was really designed for stream processing, or you can do stream processing in a database way. So we open sourced the project in April 2022 under Apache 2.0 license. And over the last 1 year, we have already gathered 5,000 GitHub stars and 130 GitHub contributors. We have already had 1,000 Slack community members, and the system has already been deployed by over 100K times. So let's talk about stream processing. So every time we mention stream processing, you may think about applications like real-time applications like edge recommendation, network monitoring, stock dashboarding, and many others. So in these applications, this kind of application can generate huge amount of streaming data. And typically, we use either the operational databases like MySQL and Postgres, or use the messaging queues like Kinesis, Kafka, Rapanda, and many others to consume the data from the applications and store the data there. And then afterwards, we want to do some real-time analytics and probably extract the real-time insights from the streaming data. But neither operational databases nor messaging queues can do that. So how do we do that? That's why people need to use a stream processing system like Rising Wave, Flink, KTDB, Samza, and many others. So stream processing systems continuously process large volume data, and actually it's streaming data. The key point here that the processing and the computation is continuous. It will never end, right? So the key challenge here that it's not about we do continuous filtering or continuous group by or continuous filtering or continuous projection. It's more about how we can handle complex queries like joins and aggregations. Why? Because when handling such kind of complex operations like joins and aggregations, we need to think about how do we manage the internal states, because we need to measure internal states which can support the incremental computation. So if you have never heard about the state management, or if you just want to recap what it is, then just think about we want to join two data streams. One is the impression stream, and the other one is a click stream. And this is a pretty standard ad monetization use case. So if we want to consume these two streams and join them together, then essentially we need to maintain two states. One is the hash table for the impression stream, and the other state is the hash table for the click stream. So every time a new tuple comes in from, let's say, the impression stream, then we need to, we will consume the tuple and then check, okay, whether there's a match in the hash tuple for the click stream. If there's a match, then we just, deliver the result. Similarly, if there's a new event comes in into the click stream, then we also need to do the same thing for the check and do the check on the hash tuple for the impression stream and generate the result accordingly. So if we just need to maintain a state, then it's we probably can just use, let's say, RuxDB or some other keyword stores to do that. But the challenge here is that, first, the state can, in a stream processing scenario, we can confront the workload spikes, right? We probably in a sudden we need to consume large amount of data. That will be a problem, right? And second, in the stream processing systems, most of the time we actually use distributed system. Then the problem comes that, what will happen if one of the nodes failed, and what will happen if, let's say, we come from the workload burst, and we want, how do we do the scaling, right? Conventionally, so that's the problem that the problem introduced. That is how we want to manage the internal state. So conventionally, what people does is that we use the MapReduce style computation model, which means that essentially we couple the compute and storage. Basically, let's say that we have 3 machines trying to run this streaming processing job. Then essentially, and now we have 3 machines. Then essentially, we're partition the state into 3 pieces, and then shuffle them into 3 different machines. So that for every single machine, they only need to take care about their local state. They do not need to communicate with the other states. Well, it works well, and until, we confront the workload spike. Once the workload spikes incurs, then we will know that the state will increase. Then the problem becomes that for every single machine, the state may increase. And probably because of the workload screw, right? One single machine can consume more data, and it can probably need to support more workload. And because of this, probably we can come from to the machine crash just because of the out of memory or running out of the storage. So how do we solve this problem? Well, if we now build a new system in the cloud, then probably people will think that, we can leverage the cloud native architecture, right? We can essentially leverage what we have in the cloud, which is the decoupled compute and decoupled storage service. So yeah, when we build a new streaming systems, we can definitely use the decoupled compute and storage architecture to build a service. And actually, many systems have already done this. For example, in the Alibaba Cloud's Flink service, where they have their own hosted service, they actually adopted this so-called decoupled computing and storage architecture to enhance their Flink service. In Rising Wave, we do exactly the same thing. We use the so-called decoupled computer architecture to ensure that the computing and storage can scale in and out independently and infinitely. And there are some other systems that adopt the same thing, and I believe that's in the next generation of database systems. Most of the stream processing systems will do exactly the same thing. So, what will happen if we adopt this architecture? Then go back to this, the ad monetization example. We have 2 streams, and we need to maintain 2 states. So we can just put these 2 states in S3, so that whenever the workload fluctuates, we do not really need to care about what we need to do. We do not need to take care too much care about how to deal with the state, because where the state is in S3, and S3 can scale in and out independently and infinitely without our attention, right? Because that's a service. Well, The idea is great. Well, if we put everything in S3, then we do not need to take care of the scaling and out. But the problem here is that S3 actually has super high latency. The latency can be as high as 100 milliseconds. Think about that. Okay, if you want to run a stream processing job, and for every single time we access the state, it will incur 100 milliseconds. Then just imagine that what will happen if we have, let's say, 10 accesses in 1 second. Well, the stream processing system will not work because the latency will get higher and higher, and we will find that okay, it can never consume all these data events, right? Streaming data events. So how to mitigate this problem? Well, I believe that many people will think about, okay, look, we can probably use secure storage, which is pretty classic mechanism in the cloud system. Well, in the cloud, what do we have? We have not just the EC2, not just the S3. We also have the EBS, right? So essentially, we have different storage and different type of storage. In EC2, we have the local storage, which can be considered as a cloud cache. EC2's local storage is super fast, but the problem here is that the data will get lost if the machine crashes. And we also definitely have S3, and the S3 is persistent storage and it's super slow, but it provides a level 9 of durability. And in the middle of EC2 and S3, we actually also have the EBS. And the EBS you can consider like cloud disk. Well, it's a disk, and it's fast, but it's not as fast as EC2's local storage. But the problem here is that but the advantage compared to the EC2's local storage is that it actually provides 5 nines durability, meaning that if your local machine crashes, then we can still recover from the EBS. Well, but definitely, it's like if we have this kind of like say different devices, then obviously we can keep all our hot data in the EC2 and cold data in S3, and potentially put a warm data, so-called warm data, in EBS. Which this kind of architecture is pretty classic. Well, but one question we would raise is that should we really leverage EBS? Well, at least based on our experience, our answer is no, at least for now. Why? Well, I think there are several reasons. The first one is that EBS is actually more expensive than EC2's local storage, and which can be kind of surprising because EBS performance is not that great, but it does provide durability, and people have to pay for that because that's a key feature of the EBS. And second thing here that EBS is slower than EC2's local storage, and because if it's local, if it's slower than EC2's local storage, then in a stream processing system, which is very sensitive to latency, then leveraging EBS can be a challenge. Definitely can be a challenge. Well, EBS is persistent, which means that it actually provides some benefits when we want to recover the system or we want to migrate the system to other machines also to do scaling and out. But again, for now, we think that we don't really have a very good answer to how to leverage EBS in the stream processing system. Okay. Anyways, we need to use secure storage. Then the problem here is that how to manage the data at different layers. Well, we have the local cache, local recent data. We can store the recently accessed data in a local machine, and the persistent data or some older data in S3, right? Then how do we manage the data? Well, obviously the answer is we can use the log structure merge tree, which is not quite surprising, right? Log structure merge tree is like it's a hierarchical tree structure. You will need to the algorithm tree will continuously compact the local runs the so-called lower level runs, let's say in this case, right, the runs in level 0 to the next level, which is level 1. And as we gather more data in level 1, we will gradually compact that data into that next level, which is level 2, so that we can essentially continuously and gradually move the data from the local machine to the S3. That's how the things work. Yeah, this picture actually shows well the compaction and all the internal structure of the LSM tree. Well, LSM tree is great because well, it allows us to move data. But the challenge here is that the compaction inside of the LSM tree can cause huge latency spikes. Because if we run the stream processing job in local machine, the stream processing job computation can consume CPU cycles, and the compaction also can consume CPU cycles. If we put the compaction node in a compaction process in the same machine as the computation process, then we can imagine that there will be high latency spike, right? How do we do that? How do we solve the problem? Well, we can essentially move the compaction to remote machines. We can just use more machines to do compaction. But even if we do compaction in remote machines, there will be problem. Think about, okay, if we shift some data from your local machine to a remote machine and ask this remote machine to do compaction, then the problem here is that, essentially we have some cycles the compaction cycles can be wasted because during the compaction, we do this compaction in local machine, in remote machine, and the machine doesn't really send out the data to the local machine, so that your local machine cannot consume the compacted data. How do we solve the problem? Well, what we can do is that we can actually essentially partition the so-called the SST in LSM tree to smaller pieces, and so that we can streamline the upload. We can actually streamline the compaction and streamline the shipping from the remote machine to the local machine, so that we can consume as much cycle as possible. We can utilize as much cycle as possible to ensure that there's no time wasted, no resource, either this compaction resource and also the IO resource wasted. The other challenge we found is that accessing S3 is also pretty expensive. And this is because, definitely is pretty expensive because S3 the latency is expensive, and S3 actually have some certain limit to limit your access, which means that if you access S3 too often, then there will be some limitations. So S3 actually groups the data into buckets, right? But based on the documentation, you can actually have certain limits. Well, can only access 3,500 put, copy, post, delete, or 5,500 get and hand requests per second to S3 prefix, which means that if you exceed that number, well, then the performance will degrade. So that will be a problem. So how we solve the problem? Well, we think that if we just use one single bucket to host all the data, then the problem here is that we can potentially confront performance limit. But if we use too many buckets, then it will essentially cause the fragmentation issue, which means that the data is scattered across different buckets, right, which is not good. So what we do is that we will set a number of buckets to a magic number and scale and reset the number of buckets based on the workload. And in this way, we can guarantee we will not confront any performance limitation, and there will be no fragmentation issue. All right, to summarize my talk, state management is definitely a very challenging problem in the stream processing systems. And the people adopted so-called compute and storage, decoupled compute and storage architecture to achieve infinite and independent scaling of both computation and storage. We can definitely leverage tier storage to help optimize the performance. And we can also use remote compaction and streaming compaction or streaming line compaction to optimize the network and the CPU. So we to further address the performance limit problem in S3, we set a number of buckets wisely to reduce the S3's access bottleneck. Well, thanks. That's all my talk. If you are interested in learning more about stream processing or probably learning more about streaming database like Rising Wave, feel free to contact me either in Twitter or in GitHub or in our Slack community channel. I'm Yingjun Wu, and I'm from Rising Wave Labs. Thanks.